Okay, so right off the bat, I removed some of the comments I added and AI added from the last video. I did use AI to help aid me in making the last video, um, but I also used my own personal resources, books, websites, my own mind. Again, this is just for learning. This isn't like a legit thing, so relax. I added this new multiply matrix line function because I didn't like us repeating ourselves and continuously having to write multiply matrix twice for A and B. So I made a new line here from A to B and then changed this out. So we have this function call. Instead of having to call the function twice, we can just call it once. And down here, I made a few changes as well. And I changed so that every time we hit R, it responds with the event listener instead of it responding in the game loop. So it's not so weird. I could have done that last time, but I was just too lazy. And you can see how that looks. So the clicking is better. I can still move around. Everything's the same. Okay, so what we're going to change in the code we have here is, in the last video I mentioned how when we were rotating the cube that you could get gimbal lock, and that's when two axes align when you're rotating, and it causes issues. I can show a visual here so that you can see what that looks like. And obviously that's not a good thing. Most like game engines and stuff usually use Quanternions and whatnot. So we're going to implement that. There's two resources that I recommend looking at when learning about Quanternions. One is 3 Blue 1 Brown's video on visualizing Quanternions. It's pretty good. And another is a book that just talks about 3D math, and it's Mathematics for Computer Graphics by John Vince. That does a good breakdown and of Quaternions and a lot of other things concerning 3D graphics. What is a Quaternion? A Quaternion is kind of like a complex number, where a complex number represented things in a 2D space. Quaternions represent things in 4D space. And it has imaginary parts, kind of like a complex number had an imaginary part, so does Quaternions. And similar to complex numbers where there's a real and an imaginary part, Quaternions have the same thing, where there's a real and imaginary part. And it takes the form of w plus xi plus yj plus zk. And you can see here that there's one scalar part and the vector part. The scalar part is the real part, and the vector part is the imaginary part. And this is a good image I took from the 3 Blue 1 Brown video, where it shows the unit sphere. With complex numbers, we had a unit circle. With our 4D Quaternions, we have a unit sphere. And when you can see here, when 1 is the real number and everything else is 0, we see we're in the center of the unit sphere. And we have I as one axis. So, I is our x-axis. J is our, y-axis. And K is our z-axis. Just an important thing to point out, we're going to be using the ordered pair version for Quaternions because that's how the math is going to work in our program, whereas the first part of the ordered pair is the real part, and the second part is the vector or imaginary part. Then we also have unit Quaternions. A unit Quaternion is when there's 0 in the first part of the ordered pair, and then there's a unit vector in the imaginary part of the ordered pair. And there's a special thing that happens when you multiply a unit Quaternion by a Quaternion. You get some kind of rotation here by 90 degrees at a time. So if you take let's say the unit Quaternion I and multiply it by some Quaternion, I being a magnitude of 1 in the positive I direction, you can use the right hand rule to figure out what kind of rotation is happening. So if you take your thumb, you point it in the direction of the left side of the multiplication. In this case, it's I, so we're going to point it in the I direction, right? You can look at this visual from 3 Blue, 1 Brown's video. And that one circle is rotating in this positive I direction. Another circle is rotating where your fingers are curling from J to K. All right, so now this is where the fun part starts. Let's say we want to take some rotation and we're multiplying a unit vector by some quaternion. So let's say we have a unit vector and we're multiplying it by wherever the origin is of that rotation. In this case, we'll say it's the center of our 3D world, which is going to be when the real part is 1 and the imaginary part, the vector part, is all 0. So we're going to multiply our unit vector, let's say 1 in the x, y, or z direction, wherever we want, times our origin, which is going to be 1, and then all the vector part just being 0 for I, j, and k. So we can take that rotation and apply it to an object we already have, and we can use this formula right here, where p is basically the position of the object we already have, and q is our rotation. So we take q times p times the inverse of q. So we're going to be getting our inverse quaternion actually from the conjugate, which sounds a little weird. But this is the simplest way we can do it in our program. So the conjugate, if to get the conjugate of a quaternion, all you do is take the vector part and basically set the x, y, and z part of it to negative. And if the conjugate, if there's a case where if q is the unit quaternion, then the conjugate of that unit quaternion is the exact same as the inverse, so makes it easy. If we want to rotate a quaternion by a specific angle, we can use this formula. And in our code, we're going to modify this formula a little bit. We're going to take that second part of that ordered pair you see here, the sine part, and multiply all of that by an axis we want to rotate by, so that we're rotating on a specific axis that we can choose. Finally, let's get into the code. You can see all the quaternion math I added here, right here. We have a quat from axis angle, so we're getting a quaternion from an axis angle. I literally just showed you that earlier. Here's our axis that we're, putting our rotating our quaternion on, or what angle we want our quaternion to be on. This is our multiplying quaternions. I didn't show the formula for that, but I'll show it up here. This is our conjugate, getting our conjugate, our rotation, and this function right here is what I mentioned earlier, the q times p times the inverse of q. What I'll point out here is you can notice that we have 0 for the real part of our quaternion. That's because we want to be on the unit sphere. When the real part's 0, we're on the unit sphere. In our frame function, I made some changes. I have this q variable, and 1 is for the real part and 0 for the imaginary part. Remember what I said when we have a quaternion like this, that it's in the very center of our 3D space? So just remember that. Keep that in your head. And below that, I moved this switch where when you press the R and it rotates, I moved it above this for loop. And we're applying our quaternion math in order to apply our rotation by a specific angle. And we're multiplying, in each one of these cases for the switch loop, we're multiplying our unit quaternion by our origin. So we're getting a rotation of that origin, if you can remember what I mentioned before. And so we just keep, every time we're multiplying, we're applying this rotation. and then we're applying it by the angle that we're specifying here. Further below in our loop for our vectors for our object, you can see some changes that were made. We don't have that switch statement anymore. We're using the quat rotate vector function, and we're taking what was applied, the rotation that was applied to the quaternion, and now applying that rotation to the object with this function. Now, if we take a look at our program, you can see everything looks pretty much the same. We're getting the exact same rotations we had before. The only difference is we're not going to have gimble lock.